Search insert position. Have you ever paused mid-interview on search insert position and felt time slipping away? This Pattern Mastery 100 Classic shows up at phone screens constantly, and it quietly filters out candidates who can't reason about sorted arrays and binary search under pressure. Today, we'll master it with the basic framework: fast, clear, and interview ready. Let's nail it so you never hesitate again. Breakdown. We're given a sorted array nums, no duplicates, and a target. If target exists, return its index. If not, return the index where it should be inserted to keep the array sorted. Edge cases. Target smaller than the first item, return 0. Larger than the last, return len nums. Assess. A brute force linear scan is ON. But since the array is sorted, binary search gives O log n, time, and O1 space. That's the right trade-off in the expected interview move. Watch for the not found case. Return the left pointer when the loop finishes. Structure. Here's the plan. Initialize left equals 0, right equals n1. While left less than equals right, compute mid. If nums mid equals target, return mid. If nums mid less than target, move left equals mid plus 1. Else move right equals mid, 1. If we exit the loop, left is exactly the index where target belongs. Solution 1. Linear scan, ON time complexity. ON. We start by defining a class called solution. It simply organizes our method in a clean structure. This defines our function search insert, which checks where a target value should go inside a sorted list. If the target is already there, great, we return its exact position. If not, we return the position where it should be inserted. We begin a loop that scans through the list one element at a time. This runs at most n times ON. We're doing a simple left to right check. At each position I, we check, is the current number greater than or equal to the target? If yes, that means the target belongs right here, either because it matches or should be inserted before this number. So if we find such a spot, we return I as the correct index for the target. And if we finish scanning the entire list without finding a place where nums I greater than or equal to target, that means the target is larger than every element in the list. So the correct position is at the very end, index len nums. Final wrap-up. And that's how this algorithm works. It first walks through the array from left to right, then returns the first spot where the target fits, or the end if no such spot exists. Efficient, simple, and elegant. Test case check, search insert position, linear scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 5. This array represents a sorted list of numbers, and our goal is to find the index where the target 5 should appear, either because it's already present or because it should be inserted there to keep the list sorted. Here's why the solution works. We simply scan through the array from left to right. As soon as we encounter a number that is greater than or equal to the target, we return that index, because that's where the target fits in sorted order. And that's exactly what our program outputs, too. This matches the expected result and confirms that the search logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the correct index for the target within a sorted array, simple, accurate, and reliable. Solution 2, ON. Find the first element greater than target while scanning backward. Time complexity, ON. We begin by defining a class called solution. This is just a clean container for our method. This defines our function search insert, which determines where a target number belongs inside a sorted list. We start a loop that scans the list backward, from the last index down to 0. This loop still takes ON time in the worst case, but scanning from the back gives us a neat shortcut. If the target is large, we'll find its spot faster. First, we check if the current number exactly matches the target. If so, we've found the correct index. If there's an exact match, we return that index immediately. If the current number is smaller than the target, that means the target should be inserted right after this index, because everything to the right is even larger. So if nums I is smaller, we return I plus 1 as the correct insertion point. If we finish the entire backward scan and none of the conditions triggered, that means the target is smaller than every item in the list. So the correct position is the very beginning, index 0. Final wrap-up. And that's how this algorithm works. It first scans backward to quickly find where the target fits, then returns the matching index or the insertion point depending on comparisons. Efficient, simple, and elegant. Test case check, search insert position, reverse scan. Let's test our function using this input. Nums equals 1, 3, 5, 6, and target equals 2. These numbers represent a sorted array, and our goal is to find the correct index where the target value 2 should be inserted while keeping the array sorted. Here's why the solution works. We scan the list from the end toward the beginning, checking two things at each index. If nums I equals the target, return that index immediately. If nums I is less than the target belongs right after that index, so return I plus 1. And that's exactly what our program outputs. 1. The output matches the expected result, confirming the reverse scan logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully finds the correct insert position in a sorted array by scanning from the end, efficient, accurate, and reliable. Search insert position. Let's do a recap. Ever freeze up on a binary search question during an interview? Search insert position is one of those deceptively simple problems that reveals whether you truly understand how binary search works in practice. Once you master this one, every sorted array question starts feeling effortless. Breakdown recap. Conceptually, the task is straightforward. You're given a sorted array and a target value. If the target exists, return its index. If not, figure out where it should be inserted to keep the array sorted. It's all about finding the right position, quickly and accurately. Assess recap. We compared a linear scan to binary search. The linear approach works but costs ON time. Since the array is already sorted, binary search is the smart move. It cuts the problem down to O log n, time with constant space. The key detail? When the target isn't found, the left pointer naturally lands exactly where the target belongs. Structure recap. We built the logic around the standard binary search pattern. Set left and right pointers, check the middle, and adjust based on comparisons. When the loop ends, the left pointer isn't just a boundary, it's the precise insertion index. Clean, efficient, and guaranteed to work for all cases. Implement recap. We implemented the plan step by step and ran the function on LeetCode. The code executed smoothly, no syntax issues, no edge case errors. The binary search logic performed exactly as intended. Check recap. All test cases passed. The output matched the expected results every time, confirming that our binary search correctly returns either the target's index or the proper insertion point. Closing insight. The big takeaway? Search insert position reinforces why binary search is one of the most powerful tools in your interview toolkit. Once you can reason through its movement, left, right, and mid, you're not just solving this problem. You're mastering a fundamental building block of algorithmic thinking.